This video is a demo for the Sampling and Aliasing lab. It corresponds to Lab 3, Sampling and Aliasing, which is Chapter 14 of Applied Analog Electronics. Okay, the purpose of this lab is, unlike most labs you're doing, not a design lab and not even a measurement lab. The purpose of this lab is to collect data for you for writing a tutorial. You're going to write a tutorial about sampling and aliasing. And to illustrate that tutorial, you will need a lot of graphs. And those graphs are going to come from the data you collect in this lab. Now, obviously, since you are writing the tutorial, you're going to need graphs that illustrate the points you want to make in the tutorial. And that means that not everybody's going to have the same data, the same graphs, because not everybody's going to be doing their tutorials the same way. Your audience for the tutorial is somebody much like yourself, but who doesn't understand aliasing. And so you're trying to teach them what aliasing is and illustrate it with examples that'll make it clear to them. Okay, let's look first at our physical setup for this. We're going to have a breadboard. We're going to have the TeamCLC running Teradek. We're going to have USB cable there to connect it up to our computer. And we're going to have an Analog Discovery 2 being used as a function generator. Okay, so the function generator has two wires coming out of it. One is a ground wire, and we'll need to hook that up to the ground here of the TeamCLC. You can see that the ground wire here is connected up by a black wire over to that long blue part there, and that's then connected to the ground from the Analog Discovery 2. The other wire, the yellow wire here, that's waveform generator 1, we will hook up eventually to the pin that's A0 on the TeamCLC so we can record what is coming out of the waveform generator. But we're not going to do that right away. The reason is that the TeamCLC will only accept on its pins voltages between 0 and 3.3 volts. If you put on voltages outside that range, then you can damage the TeamCLC. So we want to make sure that the Analog Discovery 2 doesn't put voltages outside that range. How do we do that? Well, we can go back to looking at the waveforms program and set up the waveform generator. Now there's several things we can do here. First thing to notice is that the default when you set it up says something like a kilohertz and amplitude plus or minus a volt, offset 0, so it goes from plus 1 volt here down to minus 1 volt here. That's outside the range that we can accept. We have to move that up. Well, we could move that up. Let's say we set the offset to be 1.6 volts. Now it goes from 0.6 volts to 2.6 volts. That's fine. If you want to make it a little bit bigger signal, you can. We could say make the amplitude 1.5 volts. And now it goes from 0.1 volt to 3.1 volts. And that's fine. In fact, why don't we just leave it there? But you can play around with that a little bit. Just make sure that it's above 0 for the smallest value and below 3.3 for the biggest one. You don't want to go exactly to the rails because, for one thing, the 3.3 volts on the Teradek may not be exactly the same thing as the 3.3 volts on the Analog Discovery 2. They may be calibrated differently. So leaving 1/10 of a volt or so there allows for differences in calibration. The Analog Discovery 2 is probably a good deal more accurate on its calibration of voltages than Teradek, because the TeamCLC board I think has only got like a 5% or something guarantee on its voltage. Okay, there's a problem with doing sine wave as examples, and that is a lot of times when we're talking about aliasing, we want to talk about negative frequencies, which is a left-right reversal of the signal here. And if I just did a left-right reversal of a sine wave, then I'd be going down and up. And I couldn't tell that any different from a vertical flipping of the thing. Negating the voltage would look the same thing as negating the time. And yet I want to be able to distinguish positive frequencies from negative frequencies. It's a different phenomenon flipping left and right than flipping top and bottom. So I want to pick an asymmetric signal. And luckily, the function generator can do a whole bunch of different signals. One way you can get a nice asymmetric signal that's easy to tell what's going on is to do something like a ramp up and change the symmetry here from 100% to 50%. Now if I flip the thing vertically, it's going to have a ramp down and a flat spot on the bottom. But if I flip the thing horizontally, so getting a negative frequency instead of a negative amplitude, I'll still have the flat spot on the top with the ramp down. So ramp up changes to ramp down when you negate, but the flat spot only changes whether it's on the top or the bottom if you negate on the voltage axis. If you negate on the time axis, it doesn't move where that flat spot is. So this signal is a nice one for being able to distinguish time reversal from voltage reversal. Okay, let's go back to the physical object here and hook up that yellow wire now that we know that it's going to be safe. Okay, that's hooked up. I need to start Teradek and start the waveform generator and see what's going on. So let's go back to the screen here. I've got a command line here that's in the directory where Teradek is installed, and I can just say Python DAQ there, and if everything works right, it'll bring up a little box up here that says Teradek, select a device, and it has got a device there for me to select, so I just say go, and it connects to that and says, okay, I'm ready to run. So what do we want to do? Well, we want to sample something at a fairly high speed and also at a low speed. The sampling at a fairly high speed gives us an ability to say this is what our signal sort of really is, and sampling at a low speed then would give us what happens when we alias from having a low sampling frequency. So let's pick a sampling frequency that's a fairly comfortable one for Teradek, say 200 Hertz. All right, I will add 2 channels, but I want both channels to be looking at A0. So I'll go down to this one and say, look at A0. So both of these are now looking at the same pin. They'd be recording the same data. I want to change this one, though, to downsample. And I want to downsample by a factor of 20. Okay. How are we doing on that? We've got 200 Hertz here. So channel 1 is sampled at 200 Hertz. But channel 2, only once every 20 times that channel 1 takes a sample, does channel 2 take a sample. So it's sampling not at 200 Hertz, but at a 20 of that, at 10 Hertz. All right. So let's go back to the waveform generator. And my frequency here is a kilohertz. That's way faster than my sampling rate. I'm never going to be able to see what's going on with that. So let's take this way down. Let's take it down, say, to 6 Hertz. Okay, and you can see that the period changed when I did that. All right, so we can start running this. The thing is, the voltage range here is safe. It's still 0.1 to 3.1. I can start running that, and I can come over here and say, let's start recording this. And you can see that these 2 waveforms look very different. The one on top looks pretty much like the ramp and flat spot that we expected to see. The one on the bottom looks very different. Okay, that's way more data than you would need for any of these. So what I would do up here is put in the notes that this is WaveGen 6 Hertz ramp up 50% symmetry and 1.6 volts plus or minus 1.5 volts. Okay, those notes tell me what signal I was actually recording. And when I save this thing, I would save it with something like 6 Hertz at, let's type that better, 6 Hertz, 200 Hertz, 10 Hertz. Which is not a great name, but it will allow me later on when I go, hey, I got a data file in here somewhere that has, this frequency signal, this sampling rate, this other sampling rate. I can now go and find that one. And I can then look in the notes, which will be recorded with the data of the file, to make sure that it's the one that I thought it was. So come up with perhaps a better naming convention than the one I just used, because that one was not all that mnemonic. Come up with a naming convention for your files so you'll be able to find them again when you need to do your illustrations. And then you can go through and say, okay, 6 hertz, that did something interesting. What happens if I pick 10 hertz? Okay, so I clear this data, record for a bit, and then I can save it. And this is, I just made a mistake. I don't want to save that because this still says 6 hertz. I want to fix that. Now that I've got the right information in my notes, I can save that and say that this is 10 hertz, 200 hertz, 10 hertz. And you notice there's something very strange going on here, that this second channel looks like it's not doing anything. But if you think about what's supposed to be happening here, I have a 10 hertz signal here, and I'm sampling at 10 hertz here. So every time I sample, I'm in the same place in this waveform. And that's why it's coming out as a DC signal here at 1.3 volts. That 1.3 volts, incidentally, is just happenstance. If I clear the data and record again, it comes out as 0.5 volts. Clear the data, record again, comes out as 1.89 volts. It's just randomly, when I started it, where was it in the waveform? That's the place it keeps recording over and over again. So you're not going to always get the same value here. If you get a 10 hertz alias down to 0 hertz, you don't know where the DC value is going to be because you don't know what the phase is going to be. But you know it's going to be constant. Okay, what your job is to do is to collect a whole bunch of data like this and use it to illustrate your story. I'll do a separate video on the other part of this lab.